Okay, Chuck, I think we just got the go-ahead from Carrie. So do you want to share your screen to make sure we...
Let me go back into here.
Jay, can you see us and hear us? I don't see any other participants. Okay. All right. So we have Chuck's screen. So hello, everyone. It's a pleasure to be here with you all today. And thank you, MTERA, for hosting an incredible event and for all the work that you do. It's a real pleasure to be working with you. My name is Liz Weber, and I'm a program lead in NREL's Energy Security and Resilience Center, and also a lead for NREL's state, local, and tribal program. For this session, I would like to introduce Chuck Kurnick. Chuck is a senior engineer at NREL's Energy Security and Resilience Center and the weatherization program lead for NREL's state, local, and tribal program. We're lucky with broad support from the Department of Energy. NREL's state, local, and tribal program supports the development of efficient, affordable, and resilient energy systems that address local energy challenges. So today, Chuck will present on distributed generation and microgrids. And since we're seeing that because of the increasing cost-effective nature of distributed generation, the passage of favorable policies and new funding opportunities through bill, and increased resiliency and security that comes with DG, microgrid projects are becoming more prevalent and may be the next step towards increased energy sovereignty. So Chuck, I welcome you. Thank you.
Okay, thanks a lot, Liz. Good afternoon, everyone. My name is Chuck Kurnick. I'm a senior engineer with the National Renewable Energy Laboratory in Golden, Colorado, coming to you from my home office in Longmont, Colorado. And today I will be talking about microgrids and distributed generation. So my presentation is set up in a few sections here. So we'll talk about what is a microgrid, how is a microgrid designed, microgrid concepts, microgrid components, and a short summary. So first of all, what is a microgrid? So a wordy slide here, but this is DOE's official definition of microgrid. It's a group of interconnected loads and distributed energy resources within clearly defined electrical boundaries that acts as a single controllable entity with respect to the grid. A microgrid can connect and disconnect from the grid to enable it to operate in both grid-connected or island mode. So today we're going to be talking about all of these things, the interconnected loads, distributed resources, clearly defined electrical boundaries, a single controllable entity, connecting and disconnecting from the grid, and operating in both utility and island mode. And so in remote communities, the microgrid may operate always isolated from the grid. So think about Alaska, for example, remote villages in Alaska. So microgrid applications, commercial, these are kind of some common use cases that we've seen. So commercial and industrial, it's built for reducing costs during grid-tied operations, and it will also provide backup power to critical facilities in the event of a utility outage. A community or city utility microgrid, that might be used to improve reliability or emission and energy targets. It may be used to back up critical facilities during an outage of the larger grid. Say if you've got public safety or a community center that you want to keep operating, a hospital, that sort of thing. And then in rural communities on islands or in Alaska where there may not be any grid connection. If there is a grid connection, a microgrid may be used to offset fuel costs and increase resiliency. So microgrid benefits. Reliability is the first one that people think of. It's basically, a microgrid is basically a backup system to the utility grid. You can also use a diversity of fuel sources, such as renewables or diesel or natural gas generation. There are economic services that you can get from a microgrid. So grid-tied services, those might be ancillary services such as voltage or frequency regulation, peak shaving, load shifting, things you can do to reduce your energy bill. And it can also enable additional renewable production. Some other benefits might be improved power quality. So if you see blips from your utility, this may be, or even longer outages, it may be able to improve those. You can, it makes it a little bit easier to integrate combined heat and power. So this might be one of your primary sources when your utility power goes out and you need to be in island mode. And it can also enable electrification. So challenges with microgrids. Renewables are highly variable. Frequently, this is a primary source in a microgrid would be renewables such as solar or wind. And renewables require a backup source. So integrating a lot of renewables can present a challenge. Stability and control. Controls are really complex for these, for microgrids. You know, as we saw in our definition, getting this entire entity to operate, you know, all of these sources and loads together to operate as a single entity, that can be pretty complex. It's also challenging because microgrids are generally referred to as a weak grid. And so that means that it's susceptible to disturbances from a large load being added to or removed from the grid. And this is typically due to the smaller sources that a microgrid is operating with. And then there can be complications with protection. So your protection modes, your circuit breakers and that sort of thing, those need to have different values, whether you're grid tied or in operating in island mode. And so that can be challenging. Also, valuing resiliency can be a challenge. So one way that we've been thinking about it is through something called a customer damage function. And so if that's sort of easy to think about if you think about like a manufacturing facility. If that loses power, you've lost production for a certain amount of time for the time of the grid outage. You've also, you may have people that you need to keep paying for, you know, a few hours during the grid outage. And you may even damage some of your equipment during that outage. So that insurance companies can think about that. You know, it's pretty easy for them to think about that. But when we start thinking about what's the value of resiliency when a community loses power for a few hours or for a day, it's a little bit harder to assign values to those. We know that resilience is a benefit, but it's just harder to assign economic values in kind of the world we're operating in today. And then regulatory challenges. There can be regulatory challenges. So a high renewables percentage can sometimes cause problems for a utility grid depending on the circumstances. Synchronizing, if you're planning to operate in grid tied mode, operating your sources in parallel with the grid can be challenging. And then utility tariffs. So you might have limited tariffs to deal with the microgrid. And so how is a microgrid designed? So first we've got, there's a few different phases. You've got inputs, the analysis, and then the outcomes. And so inputs are things like your mission goals. So for example, are you backing up a hospital or a community center or maybe public safety offices? Your utility rate structure, you need to know this so you can do your analysis. Historic and projected load data. We always look for 15-minute or maybe hourly load data. So that would be at your main meter. You'd want to have collect data every hour to look at what your kilowatt hour usage and your kilowatt usage is. That makes the analysis much more accurate. We can come up with a design that's more applicable. And then looking at the location and the renewable energy potential, you know, so some places may have a better wind resource, some places may have a better solar resource, some places may be near a landfill where a mature landfill where that's starting to produce natural methane. So, you know, just understanding that sort of thing. Biomass is also an option. And so analysis, there's typically a techno-economic analysis where you're looking at sizing relative to the cost and how that might interact with your utility energy consumption. You're looking at what loads do you really want to serve when you're operating in islanded mode, and then possible solutions. So kind of conceptual designs during the analysis phase. And then the outcomes would be a much more complete design where you've got actual components, their sizes, you have a good idea of their operating mode. So for example, if you're utility tied, you may have different operating modes depending on what tariff you're using, if you've got time of use rates, or possibly high peak demand charges. So you may have different operating modes depending on what you're trying to achieve. And then in islanded mode, you also may have different operating modes. So for example, if you need to reprioritize your loads just based on the amount of energy that's available, or what's most important at that particular time if you can't meet all of your loads. And analysis. So here's some of the things that we think about when we're doing a microgrid analysis. So on the left, we've got the load and renewables data. So we're looking at the daily profile of loads in these two graphs here. So at the top is this is a typical commercial load profile. So you can see that there's higher peaks on weekdays here, lower peaks on the weekend, which is what you might expect in a office building where people are coming to work each day. And then this is a yearly profile, the annual profile. So you can see that it's got higher peaks and averages in the summer. So this is all information that you would use in designing your microgrid, sizing your components and your sources. So again, really important to have the load information when starting off on a microgrid project. And then you'd also do a techno-economic analysis. And so one consideration is demand management. So frequently, utility bills might be, what's really common in commercial and industrial applications is to have a demand section of your bill and then the energy section of your bill. And so the demand section looks at what's been your peak demand over, say, a 15-minute time period. And that can be a really significant part of your bill. And so the way I think about demand is, so demand is measured in kilowatts, and your energy, so demand or power in kilowatts, and then your energy is measured in kilowatt hours. And so the way I think about demand is, and this is really oversimplified, but it just helps me kind of get my head around it. I think about the size of the conductor that's coming into your site. And so if you have a really high demand, you need to have a really big conductor. And so we know how expensive copper is. And so if you need to have a bigger conductor, that means the utility had to spend more on that conductor to get it to your site, that conductor that goes to your site. So as a result, you're going to pay more when you use more of that conductor. And so so that's a demand charge, basically. So you pay by the kilowatt hour, or I'm sorry, by the kilowatt. So you pay by the kilowatt over a 15-minute time period, and then your energy is your kilowatt hours. Everyone's pretty familiar with that with their residential bills. And so what we have here in this graph is we're looking at the brown, and that's how much power is being imported from the utility, this brown section here. And you can see that it's at kind of a stable level here. And so what we're doing the load at this site is basically the top of this graph. The very top of this graph is how much energy that site is consuming, at a particular period in time. And so the load is met first by the utility, and then they cap that at a certain point. They're trying to manage their demand, and then they're adding natural gas generation in the blue here. And then the green, the different shades of green are landfill gas. The very top here in yellow is solar, and then the red is in battery. And so what this is kind of demonstrating is the kind of the techno-economic analysis that you might go into to look at the economics of your microgrid to see if it makes sense financially. And if you have any financial benefits, in addition to any resilience benefits that you're getting. That's typically how we approach it. And so, so this is just kind of an example of how you would, of the things that go into it. And so you are sizing your components. So for example, you're sizing your natural gas generator based on the economics, based on economics here at this point. Okay, and so the next slide. So there's layers of resilience. We can think of resilience in kind of these different layers. So there's the utility side, and typically metrics that we think about for a utility, the way that they're utilities are actually kind of graded on this, SAFE and SAIDI. So SAFE is System Average Interruption Frequency Index, and SAIDI is System Average Interruption Duration Index. And so SAFE, how frequently you have outages, and then how long, what's the duration of those outages? And those are two metrics that utilities are measured on. And so if you want to increase your utility resilience, you may have multiple feeders coming into your site. And then another way to kind of increase resilience and just reduce the amount of energy you need from your utility would be have renewables. So solar and wind, other biomass or landfill gas, those are going to reduce your utility consumption. The next layer of resilience is the microgrid. So think of a microgrid, it's basically a backup for the utility. When you go from grid mode to island mode, you typically have a short outage. You need to also think about fuel delivery and availability. So for example, if you need to get propane deliveries during a snowstorm, that may not be as reliable as a pipeline, a natural gas pipeline that delivers gas right to your site. N+1 redundancy. So what that means is that components have at least one independent backup component. So if your site has a generator, PV and wind, you might have an additional generator that's not normally needed, but that would be your N+1 redundancy. It's to back up your backup generator in case that one goes down. So it's a backup to a backup. Then you need to think about if your microgrid can support the full load, for your full site load. Can it only support the critical facilities? If so, how do you make sure that only the facilities are served and nobody else is getting load? So that's something to think about when you're thinking about resilience. And then renewables, again, will extend the operation during outages, and they'll help you save fuel during an outage, so you don't need to get that many fuel deliveries. And then the last line of defense are these building generators. So one of the really important things is maintenance on backup generators. You need to make sure that you're doing your maintenance per manufacturer's recommendations. If not, and you've got a generator there and you're expecting it to work when you need it, it may not work when you need it. So maintenance is really important there. Some engineering considerations on components. So sizing, so generators, you want to think about the quantity and size. So for example, if you need a 5 megawatt generator, it might be better to get 5 1 megawatt generators rather than 1 5 megawatt generator. Generators typically have an operating range where they operate most efficiently, and so burn the least amount of fuel. And they also have kind of a minimum level of operation. So if you're trying to power your load, say at night, is 1 megawatt, and you're trying to power that load, it may be better for you to have to turn off those 3 or 4 generators and just have 1 or 2 operating. Again, redundancy is something to think about. Emissions, propane and natural gas are cleaner than diesel if you need to have fossil fuels on site. And these days, typically you need some sort of for a resilience microgrid, you do need to have some sort of fossil fuel burning device, unless you've got a solid source of, say, biomass or landfill gas as well. Renewables, so can you have central renewables or distributed renewables? PV is, you can have those PV, solar photovoltaic, you can have those either centrally in a large array, or distributed, maybe at each building level. Something like a biomass plant you'd probably just have one of those, and that would be a central resource. You need to, for PV in particular, you need to think about the AC versus DC sizing. If you need to meet a certain AC load, let's say 1 kilowatt, you'll need a slightly larger DC rated facility, because you've got to convert. PV produces power in DC, and most loads consume it in AC. when that power goes from the DC through the inverter to be converted to AC, there are losses associated with that inverter. So if you're talking to developers, you just need to think about, are they sizing a particular resource in AC or DC? And this is going to apply mostly to PV and I think wind too. And then your design life, PV has a 25-year design life, and I think it'll actually run for longer than that. But again, something else to think about. Wind might be a little bit shorter. There's O&M associated with that. So again, making sure you're doing the right O&M. Energy storage, it allows for generator off operation. If you cycle the energy storage more frequently, you'll be affecting its design life. So charge discharge cycles, that's one cycle. If you do that frequently, your design life will drop. I think we know that with our phones. As we charge them, discharge them every day, the battery gets worse and worse. Isolation devices, you need those to sectionalize the grid or to reconfigure the grid to route power where you need it. Protection in grid mode versus microgrid mode, they do require different settings because of fault current. So the grid has much higher fault current. It's got much higher sources, much larger sources. And so those sources can produce a lot more fault current versus when you're in microgrid mode, you've got much smaller sources. They can't produce as much fault current. So your circuit breakers need to be set so that they can deal with that sort of thing. And again, there's also a few studies you need to do. So coordination studies, arc flash studies, power flow studies. These are all engineering studies that need to be done when you're developing a microgrid. Data communication. So getting all of these things to behave as a single entity, you need some sort of data communication, whether that's fiber or copper. We're all familiar with the copper Ethernet. Maybe we're not all familiar with the Ethernet cables that plug into our computers. A lot of folks have Wi-Fi, so you don't need any computers or any cables to plug in. So again, data communications are a really important part. And again, thinking about the redundancy and reliability of your data communication on your site is important too for a resilience microgrid. And then utility, there's interconnection agreements. You may have a minimum import where the utility requires you to consume a certain amount of power per month, and a rate structure, so power or energy, and then a rate structure. So your tariffs, these again are all things that are going to go into the decision. Engineering considerations. So a really common way of showing an electrical system is this one line, or maybe it's called a single line diagram. You might hear both of those terms. And so what we're showing here is the point of common coupling. And so that's where your utility enters. And from that point of common coupling, the power goes through some transformers, reducing the voltage from the utility levels down to the levels on your site. It goes to this distribution bus, and then from this distribution bus, it'll go to a feeder here, and then and frequently through a transformer once it gets to the feeder, and then from the feeder, it'll go and feed loads. Well, actually, no, so here's where the transformer is. So those are some components that you'll see on a single line diagram. So transformers change the voltage again from utility entrance to the distribution bus. There'll be a step down transformer stepping down the voltage right there. Again, from the distribution bus onto the feeder to towards each of the loads or sites. You might see there's a transformer here, and so you might see a transformer depending on your neighborhood. One transformer might power 3 or 4 houses. A single commercial or industrial facility might have its own transformer. So you'll see those in the system as well. And then you've got the isolation devices. So there's a switch here to open up that you can open up to eliminate to disconnect from the utility grid. There are some switches here so that you can tie your distribution buses together depending on which utility feed you're using. There's switches at the feeder level, switches going from the feeder down to the load. So isolation devices are really important in a microgrid as well. So now a few concepts around microgrids. So again, as I mentioned earlier, a microgrid can operate in utility grid tied mode or island mode. And so on the left side, we've got kind of some characteristics of a utility grid, and on the right side, we've got characteristics of a microgrid when it's operating in island mode. And so in utility mode, the frequency is set by the microgrid. In island mode, frequency is set by a grid forming source. And so these days, that grid forming source is most likely going to be a fossil fuel generator, a rotating generator, or it could be a biomass or a landfill gas as well, but typically a rotating generator. And so that source is going to set the frequency. And the reason that's important is that photovoltaics, solar PV in particular, needs to see a grid forming source to in order to operate. If it doesn't see a grid forming source, it can't operate. And so, this frequency is set by the grid forming source in island mode. Again, in utility mode, the sources in the microgrid can operate independently. As we saw in that earlier picture, we saw kind of the natural gas generators operating after the utility hits a certain peak. And then we saw the landfill gas generators, and we saw the solar PV on top of that. So those are all kind of doing their thing to meet the load. When we're in island mode, those sources need to be operating a lot more in cahoots with each other. So you just want to make sure that they need to be talking to each other, they need to be sharing loads and that sort of thing. Utility grid mode, voltage can be impacted locally by sources. So if you've got, if we think about our one line diagram, if you had PV, a lot of PV on one of those feeders, you could be impacting the voltage on that particular feeder. And then the same with island mode, only it's a little bit more important to control that voltage, because if you've got a lot of PV on a single feeder, it could increase the voltage on that feeder, causing a problem. And so you just want to make sure you're conscious of that in microgrid mode, in both modes really, but mostly in microgrid. As we talked about earlier, under utility grid, when you're grid connected, fault current is high, fault current is low in an islanded microgrid. And then there's little impact from variables and renewables when you're grid tied, but there can be a really big impact from variable renewables and loads when you're islanded. Again, just because the utility grid is so much bigger than your grid in island mode. Okay, here, transitions from utility to island mode and island mode back to utility mode. Closed transition. So a closed transition is when you have, it's also called a seamless transition or a blinkless transition, and you're basically running in parallel with the utility. Your microgrid is running in parallel with the utility. And then once you get to, and slowly ramps up while the utility power ramps down, and once you get to zero power flow across that point of common coupling, then you can disconnect from the grid, and your customers won't even know it. Nobody on site will even know. There won't be a blink or anything. And then in this closed transition back to utility, it's basically that same thing in reverse. So you synchronize to the utility, you ramp down, you're at zero power flow, you ramp down your sources, utility starts to pick that up, and you and then you can turn down turn off your sources. An open transition, and this most frequently occurs when you're transitioning from utility. It's not that hard. Let's see, let me start over. An open transition is where you disconnect from the utility and then bring up your sources after you've disconnected from the utility. So you don't operate connected to the utility at all. And so in that scenario, you're going to have an outage. It might be 5 seconds up to 10 minutes, maybe a little bit longer, depending on how long it takes your generators to come online and bring feeders up and that sort of thing. So you typically have to bring all that up in kind of a sequence, a certain sequence, so that you're not putting too much of a load step on your generation. And so the reason that you would do an open transition, it sounds complicated, but it's doing an unplanned closed transition is really expensive and complicated. It's really challenging to do these days. And so that's why transitioning an unplanned closed transition is really hard to do. A planned closed transition can be done. You just need to make sure you've got that agreement in place with your utility. Okay, I think we're coming up on time here, and I'm got a few more slides to get through. Islanded operation examples, and so this one is a pretty good one. So on the left we have generator and PV, and so if we file this across, you know, we've got the power here on the y-axis, and on the x-axis we have time. We look here, PV starts to ramp up in the morning. The generator's been running all night to meet the night load. The load starts to ramp up in the morning. We have to keep the generator on because, remember, as I said before, the PV needs a grid forming source to operate. So we keep the generator on. We have to curtail the PV because our load is only so high. So because we have the generator running, we have to throw away some of this solar PV. And then you can see as it goes down, the generator ramps back up, load drops down a little bit, generator operates overnight, PV goes to zero production. Over on the right side here, kind of same thing, the PV starts to amp up, generator is operating overnight, so this one is PV and BESS, generator, PV, and BESS. Sorry, I'm starting to rush a little bit here. The generator is operating overnight. As the PV starts to ramp up, the generator can turn off, and it can turn off because now we've got a battery. And so that battery, that extra PV here goes into the battery. And so we're charging up the battery. As the PV starts to drop off, we can start to discharge the battery here. And then as the PV drops off all the way and the battery discharges to zero, we now have to start the generator. So in this case, the generator is off during the day and only operating at night. So that's a good way to run things if you can do that. It can get kind of expensive. So, you know, being able to have utility rate structures that can be used in this situation to justify economics would be a good thing. Okay, so microgrid components. I've talked a little bit about most of these before here, so I'm not really going to go into this slide. Power factor correction. So I'm a mechanical engineer by training, and all of this other stuff, you know, they say that you can use this electrical analogy for plumbing. I'm good with the plumbing analogy. Once we start to get to power factor, as a mechanical engineer, that starts to get a little confusing to me. It's basically how the efficiency with which electricity is used. So if we look here, we can see that real power is kind of like the beer in this mug, and then the reactive power is the foam. So it still takes up volume, it's still there, but it can't really do any real work. You'll have to look for an explainer on YouTube to get a little bit more information on that. These are some typical symbols you see on a one line. Here are some real life picture of some of these things that we've been talking about. Pole mounted transformers, fuses here, and then, you know, the conductor wires here. Neutral is, you know, maybe over here. So that's some of the components. Typical sources, we've talked about a few of these. Fuel generators can grid form. Diesels are more stable. Natural gas and propane have lower emissions. Diesels are more stable, and that's just due to the type of engines they are. Easy to load share with the right controls. Wind and PV, they can grid form. It's not very common today, and wouldn't be common, I think, in small scale systems. In larger utility scale systems, it might start to become a little bit more common. They're highly variable. You can drop their production down to just above zero if you need to. So more curtailable than a fuel generator. Hydro, we probably won't be seeing a whole lot more large scale hydro these days. It's going to be a little bit more seasonal, probably at the scales that would be used. in smaller systems. Sometimes it can be grid forming. Energy storage, there's a lot of different types of energy storage. You know, we've been talking about batteries. There's also flywheels, not quite as prevalent. Pumped hydro, you need a really big, those are typically large scale systems. Thermal energy storage is actually pretty common. You can store chilled water if you've got the right kind of chillers and the right kind of facility. And so that's, or you can store hot water if you say you've got a combined heat and power system, where you're taking the heat off of your generators and you're storing that heat somewhere for domestic hot water. This is really good for load shifting. So, you know, making cold water when the sun is shining, and then using it, running it through your buildings at night because you've got storage. When we're talking about batteries, you'll typically see two numbers associated with it, the kilowatt rating and the kilowatt hour rating. And so the kilowatt rating is determined by the size of the load you're trying to power. So if you're trying to power, say, a 10 kilowatt load, you need a 10 kilowatt battery. If you're trying to power that 10 kilowatt load for, let's say, 1 hour, you just need a 10 kilowatt hour battery. But if you're trying to power that 10 kilowatt load for 2 hours, you need a 10 kilowatt, 20 kilowatt hour battery. So make sure you need both of those numbers when you're speccing a battery, when you're talking about batteries. Energy storage, we talked a little bit about this. There are a lot of different use cases for, especially for battery energy storage systems. They just keep increasing, and balancing those and prioritizing those can all be challenging, because if you're trying to do demand management, but you want to make sure you've got power in case of an outage, you can only drop down to a certain state of charge. So this can get pretty complicated. Frequency regulation or voltage stability, we saw a lot of power, battery energy storage installed in the out east, because there was actually a market. The utilities had a market for it, so a lot of batteries got installed there. They're different than a generator, faster response time. They can be really programmed to do a lot of different things. They can absorb power, which is one of the great things about them. And again, a battery has two components. It's got the actual battery itself, but it also has an inverter. And so when I was talking about that power number, that's the inverter, the size of the inverter. So kilowatts, inverters are going to be in kilowatts. The storage, the batteries are going to be in kilowatt hours. Storage is usually DC, grids are AC. And so we have that, as I talked about before, with the inverter converting to AC, DC, you kind of have to do that. You have to do that in both directions now with a battery. AC power through the inverter converted to DC, store the power in DC in the battery, and then vice versa on the way out. Yeah, they can have really complicated controls. Several layers of control within a microgrid. And I think I just have one more slide after this. Several layers of control in the microgrid. The slowest is kind of this top level. It's looking at interactions with the larger grid. So you might get, say, a day ahead price for energy. Some utilities will do this for their commercial company customers. You'll get a day ahead price. And so from that, you can program that into your tertiary control. It'll make some decisions about what batteries to charge, what generators to run, that sort of thing. Weather also, you can get, predict forecasts for the next day. Is it going to be windy? Is it going to be sunny? Secondary control is what we think about when we think of a microgrid controller. It's looking at balancing the loads and the sources. So it really comes into its own during islanded operation, balancing loads and sources, updating set points, stepping through certain sequences, opening switches and turning on generators and off generators, that sort of thing. And then the primary controller, these embedded controls. So controls within the generator, within your battery, within your solar PV inverter, really fast, making decisions on what that particular generating asset or protective relay might be doing. These all kind of talk to each other to make sure that they're all in sync. Again, really complicated. You need to make sure you've got communications between all of these things. So in summary, microgrids are standalone or can operate with a grid. The benefits are resilience and economics primarily. Modes, they operate in grid-tied and islanded mode. Microgrid design, you want to consider economics and your resiliency requirements that lead you to determine your component sizes and locations. And then we've got all of these different components that all need to behave as a single entity. And that actually is the end of my slideshow. So, okay, thanks everyone. Sorry about that. I went over.
Thanks, Chuck. It was great. And I love the beer analogy. So thank you. I was like, oh, that actually makes sense. Couple questions I've been trying to answer the Q&A in the chat, but one that I would love to hear your thoughts on is why does PV need a grid forming source to operate?
Sure, that's a great question. So the standards, and so that's starting to change. The standards to date for residential inverters, the standards have been, I think it's IEEE 1547. I don't have that number, I don't think is right. But basically, it's a safety issue. So if there's a power outage on a particular line, the utility wants to know that your solar system is not going to be producing electricity on that line. So when the lineman goes to fix it, he won't get electric shock or worse. So that's how things operate these days. There's now work being done on grid forming inverters. And so these are going to be more common in batteries. And I think most batteries these days of a certain size do have grid forming inverters, and so they can act as that grid forming. But PV needs to see a signal or else it won't operate. It's just part of the design. And if you buy an inverter today, it might be programmed to work that way. Most likely you'll be able to update the firmware inside of it and it can work. It can change its operation.
Great. And then what are your thoughts on long duration flow batteries?
So I think they have their place. They're definitely more complicated than lithium ion batteries. There's a lot of pumps and pipes and valves and that sort of thing in these long duration flow batteries. So they are going to require more maintenance. They can't react as quickly as a lithium ion battery. So they may not be able to do things like frequency regulation as well, or maybe voltage regulation where the battery needs to react really quickly. But they can act as kind of a longer, a source over the longer term, but maybe not as much managing loads and short-term variability.
Okay, great. And then this is $1 million question that I would love to get your thoughts on from the anonymous attendee. But when do you think 100% renewable microgrids without the support of fossil fuel support will be economically viable?
Oh yeah, when batteries and PV come down to whatever that price point is. Actually, NREL might have some information about the futures, right? Don't we have a future study?
Yeah, I've been Googling on NREL's site to try to find it. And so I'll continue to look and I will share that with Jake at MTERA to share with the group.
Excellent.
So I think I captured all the questions from folks, at least in the chat, the
Okay.
Q&A chat. Carrie, I think, thanks Chuck so much. Carrie, should I hand this over to you? I know we're way over time at this point.
Yes, I'm sorry about that. But
I figured since this was the last piece of the session, we could continue recording. Jake was nice enough to let us keep going.
Thank you, Jake. Apologies.
It was great. Yeah, we're good. So thank you, Chuck and Liz. You guys were wonderful. And let's see here. I am going to put up a poll. So if everyone could just take a moment to answer our little survey. That would be great. And I think there's probably some more questions. So maybe Liz can gather some of those questions and share them with Chuck.
I sure will.
Thank you everyone for joining us today. I'm going to launch the poll. So just take a few minutes to answer our questions and have a great rest of your day.
Yeah, and thanks for letting me be a part of this. This was great.
Thank you.